So we're going to walk through some of the basics of how to solve calorimetry problems. Calorimetry is the idea of calculating the amount of energy transferred into or out of a system or between different objects. So it's all about quantifying and calculating that amount of energy. So the first thing that we need to remember is that energy can be used for two things. The first thing that it can be used for is to change the temperature, to either increase or decrease the temperature. It can also be used to change the state or the phase of a substance. So from a solid to a liquid to a gas, or vice versa, go in the other direction. Each of these require different ways to calculate energy. So now we're going to look at how we can calculate energy involved with a change in temperature. And we're going to look at how we can calculate energy involved with changing phase, and then we can look at how we can combine the two of them together. We're going to calculate energy, and we're going to use a unit called joules, which is spelled Joules, so it's different than like fancy jewels you'd wear around your neck. And the abbreviation for that is a capital J. You'll also see energy not in my problem so much. You'll see it in other places. You'll see calories. That's how we talk about energy from food. Kilocalories or kcals. And we actually have two different types of calories. We'll look into that more when we start to get to our snack food experiment. But for now, we're going to focus on energy in joules. So there is a lot of information on this board, and we're going to walk through it one step at a time. So like I said, there are two different equations depending on what type of change you're doing. If you're doing a temperature change, you're going to use Q equals mc delta T. This right here, this delta T, is the clue that we're going to be changing temperature. So if you're warming up or cooling down or changing temperature, you know that this is the equation you're going to use. Our Q is our energy, remember, and we're calculating it in joules. If it's positive, we know that we're gaining energy. If it's negative, we know that we're losing energy or it's being released from the system. Our M is just our mass, and we're going to look at mass usually in grams. Our C is a constant. It's called the specific heat capacity. And the units for that are joules per gram times degrees Celsius. Basically, your units for your specific heat capacity need to correspond to the rest of your units. So if we're going to do temperature in Kelvin, we need to convert from Kelvin to degrees Celsius if we want to use a constant with that unit. All of your units have to match. The specific heat capacity is unique to each individual substance, and we're going to look at what that number actually tells us here in a couple of minutes. And then finally, our last variable is our delta T, which delta means change. T means temperature, so our delta T means change in temperature. And we calculate that as our final temperature minus our initial temperature, so final minus initial gets us to our delta T. And we're going to use temperatures in degrees Celsius this time. Over here, we have our options for equations that we're going to use when we calculate energy involved in phase changes. Depending on the phase change depends on which type of reaction you're going to use. Really, it depends on which constant you're going to use. Both of these are Q, which is our energy, times equals mass times some constant. So Q is our energy, still in joules, means the same thing. If it's positive, it means we're gaining energy. If it's negative, it means we're losing energy. M is still our mass in grams. And if you notice, we have two other variables. We have HF and we have HV. HF is the heat of fusion. The units for that are joules per gram. And we're going to use that constant when we go between solid and liquid phases. So I always think of fusion as in you're fusing the particles together to go from a liquid to a solid. That's how I remember that one. Again, this is unique to each individual substance. HV is the heat of vaporization. And that one makes more sense. We say that we vaporize something when we're going from a liquid to a gas. So we use heat of vaporization when we're going between the liquid and the gas state. And again, it's unique to each individual substance. The units for both of these are the same. They're joules per gram. It's just a matter of which one are you going to use. Are you going to use heat of fusion or are you going to use heat of vaporization in your Q equals M times H? So like I promised, we're going to look at each of our constants. The first one we're going to look at is the specific heat capacity, so that's C. The specific heat capacity is the amount of energy in joules that you need to raise the temperature of 1 gram of a substance 1 degree Celsius. So for instance, the specific heat capacity of water is 4.18 joules per gram times degree Celsius. That means if you have 1 gram of water and you want to raise it 1 degree Celsius, you need 4.18 joules of energy. For the heat of fusion, it's very similar. It's the amount of energy required to melt 1 gram of a substance, because we know that if we're going from a solid to a liquid, we have to put energy in. So it's the amount of energy required to change 1 gram of a substance from a solid to a liquid, and also from a liquid to a solid. We can look at both ways. It's the amount of energy you get out. The heat of vaporization, HV, is the amount of energy required to boil 1 gram of a substance. So all of these are for 1 gram of a substance. For our specific heat capacity, since it's involving a change in temperature, it's changing it 1 degree Celsius. All of these constants refer to the amount of energy needed to make a certain change. So we're going to use them to help us calculate our energy that we need for more than 1 gram, or to change it more than 1 degree Celsius. So here's our first example. Calculate the amount of energy needed to warm 200 grams of water from 23 degrees Celsius to 100 degrees Celsius. So you know, since we have a temperature change, we're going to use Q equals mc delta T, because since we're involving temperatures, we know we need our equation with our temperature change. So we're calculating energy, so we know that we're going to be calculating Q. Our mass is 200 grams. It's water, so we need the specific heat for water. I will give you the constants because most of what we'll be working with will be water. If it's not water, well, regardless, I'll give you the constants that you need. So the specific heat capacity of water is 4.18 joules per gram times degrees Celsius. And then remember our delta T, this was really mass times specific heat times final minus initial, because that's really what delta T is. So our final temperature is 100 degrees Celsius, our initial is 23 degrees Celsius. When we plug all of this into our calculator, so I'm going to do my subtraction first. So copy all of that guy. 100 minus 23 is 77 degrees Celsius. So our Q is equal to, I calculated it ahead of time, 64,372 joules. So our grams canceled top and bottom, our Celsius canceled top and bottom, we were left with joules as our unit, and that makes sense because we want to calculate the amount of energy, which would be in joules. So this was just a basic plug the numbers into the equation and calculate Q. Let's look at one where we're calculating the final temperature of something. So in example 2, I say you remove 500 joules of energy from 100 grams of water at 80 degrees Celsius. What is the final temperature? So again, we're involving temperatures, so we know that we're going to use Q equals mc delta T, which is really Q equals mc times T final minus T initial. We want to solve for T final. So I'm going to rearrange my equation before I even start plugging numbers in. So I'm going to divide both sides by mc. This is just basic algebra. And so then if I want to isolate T final, I'll do T initial. And my new equation ends up being Q divided by M times C plus T initial equals T final. So now I'm going to plug my numbers in. Since I said we removed 500 joules, I'm going to put a negative 500 joules on top because negative means that it's being removed, divided by 100 grams. It's water, so we're going to do 4.18 joules per gram degrees Celsius plus our initial temperature was 80 degrees Celsius. And we get T final to be 78.8 degrees Celsius. So that would be our final answer. So notice we removed 500 joules of energy, which seems like a lot. Really, we only decreased our temperature by a little over 1 degree Celsius. Okay, let's look at an example where we're not changing the temperature. This one says, calculate the amount of energy needed to melt 150 grams of water. So since it's melting, we know we're going from a solid to a liquid, which means that we need our heat of fusion. So we're going to use Q equals mass times HF. We're calculating energy. So we're going to leave Q over here. Our mass is 150 grams. Heat of fusion for water is 334 joules per gram. Q equals 150 times 334, which is 50,100 joules of energy. So that's how much energy you would need to supply to melt 150 grams of water, just to go through the phase change. We're not increasing the temperature, that's just going from a solid to a liquid at 0 degrees Celsius. Now we're going to do one more where we're going to combine the two concepts. So this one says calculate the total amount of energy needed to boil 75 grams of water initially at 23 degrees Celsius. So the first thing I'm actually going to do is I'm going to sketch out what my heating curve would look like for this. So I'm starting at 23. We know water boils at 100 degrees Celsius. So the first thing I have to do is increase the temperature, and then I have to actually boil the water. I have to make it all turn from a liquid to a gas. So I'm going to use two things. This is going to be the MC delta T, and this is going to be the MHV. If we think about it, it's going to require a certain amount of energy to heat up the water, to increase the temperature, and it's going to require a certain amount of energy to boil the water. If we want to know the total amount of energy, all we have to do is add the two together. So we have Q would equal first how much energy we need to raise it up, so MC delta T, and then it would be how much energy we need to boil it, which would be MHV. We're using vaporization because we're going between that liquid and the gas state. Okay, so now it's just a matter of plugging our numbers in. Mass is 75 grams. Heat capacity of water, C, is 4.18. Change in temperature. Now our initial is 23. I don't tell you specifically what the final temperature would be, but we know the boiling point of water. So it would be 100 degrees Celsius minus 23 degrees Celsius. And I ran out of room, so I'm just going to drop it down here. We still have 75 grams. It's still the same mass. Our heat of vaporization for water is 2,260 joules per gram. Notice it takes a lot more energy to boil a substance than it takes to melt a substance. So now we have Q equals 75 times 4.18 times, this is 77 degrees Celsius, gets us 24,139.5 joules. And 75 times 2,260 gets us 169,500 joules. If you add them together, our total energy would be 193,639.5 joules. So this is how much energy total we would need to heat up 75 grams of water and then to completely boil 75 grams of water.